Good afternoon, my name is Jack Weiss, and today we're going to talk about a paper out of OpenAI and UC Berkeley called Geometry-Aware Neural Rendering. So the motivation is really understanding the 3D structure of the world, and here we have a couple stark examples. The consumer product Microsoft Kinect Gen 1 on the left, and a high-definition 3D laser scan on the right. But the specific goal for this paper is within a virtual 3D environment, we want to input our context images, we want to input multiple context images, and then we want to predict from a query viewpoint a query image. And so we're going to talk about a few related and comparative works, the 2D neural rendering, novel view synthesis, extreme view synthesis, and generative query network. So learning to navigate in complex environments. This is work in unsupervised reinforcement learning, in which actor-critic reinforcement learning was used to navigate a 3D maze, only using the input images and gaining rewards along the way, auxiliary rewards of apples and strawberries, and then finally your goal, which would be your final reward. So what happened was the actor-critic reinforcement learning algorithm was able to model the two-dimensional map of the maze itself. And this is work from last week, the GAN, the View-Independent Generative Adversarial Network for Novel View Synthesis. I think this was last Tuesday, so we probably don't need to go over it. But again, these two papers from last week were creating new novel views, and this is extreme view synthesis, I believe from last Thursday, and this was a paper in which we were able to do 30x magnification. So the generative query network, this is what the current paper I'm briefing is built upon. And the generative query network essentially takes multiple observations of a virtual 3D environment, and then it processes with convolutional neural network those images as well as the viewpoints for those images, and then adds them together into a neural scene representation. From this neural scene representation, then we need to generate a new image. So we take the query viewpoint as input, a latent variable z, which is a stochastic variable, and then we render, we go through our rendering steps to predict the new view. The loss is then the predicted view with the ground truth view, which we know because we're in a virtual environment. And then the loss is back propagated all the way back. So here's some good example of results from the GQN. As we can see, after training, we took a single observation, and we were able to predict multiple views from that single observation that are relatively close to ground truth. What of note is that the single observation does have all three objects in it, or else some of these other views wouldn't be possible. And we have a short video. So here, the multiple views, each view is being fed through the representation network, which is a convolution network, technically the tower network. And these various views get fed, and they have network problems. And then they get combined into a scene representation. Then from the top, we input a query view of which we want the image for that query view, and we compare it to the prediction to the ground truth. Now, what ends up happening is this essentially forces the scene representation to store enough information to produce various views from, and we're looking at free-floating camera as well as rotational camera. And so it forces how do we get back to presentation mode?
F5, hit F5.
F5? So now we're going to talk about the Epipolar generative query network architecture, which is built on top of, or is built based on the work that we just saw from the generative query network, and it uses actual components from that work, which are in blue. And so we can see here we have three context images that are fed in, and you can see them stacked, and we have our viewpoint query coming in from the top. And so these context images and their viewpoints are fed through a convolutional neural network and a representation. We'll go into more detail. They're passed to an attention mechanism and then passed down to the generation network that generates the new image with those latent random variables z, and then produces our generated output, and that's compared against ground truth for loss. Then the loss is then back propagated all the way back to the representation network with a skip connection. And we can see for this one example that it did a good bit better than the previous method. So the key contributions of this effort are the novel attention mechanism that leverages camera geometry, and that's the epipolar cross attention. 3 new data sets: disco humanoid, OpenAI block, and random room objects. Additionally, we demonstrate that the performance of the new ECA combined with components of the GQN provide us increased performance. So let's take a quick look at epipolar geometry. This is key to the method, and it's really one of the core components of how stereo vision is calculated. And so essentially, if we imagine 2 views looking at a spot in 3D space, a point in 3D space, which is our y, and then we have these 2 images corresponding to the 2 views, which are x1 and x2. If we have a ray running from v1 to y, it crosses our x1 image at point y. So what we want to understand is what is the epipolar line that corresponds in the other image to our point y. And so this is actually a linear operation using the fundamental matrix, and the key is that both v's, both viewpoints, and y form a triangular plane of which the epipolar line is on. So that gets us to our epipolar extraction, and so this is the advantage of this method. And the idea is that for each spatial point in our query, VQ is our query view. For each spatial point there, we want to find what the epipolar corresponding line is, and what those features are for that corresponding line in one of in our context image. And this is an example of a single context image. So the features from that line image, after they've been convolved, are then fed and become one of the tensors in E, and E is a 3D matrix that stores all the tensors that then get passed on for that context image associated with our query image. And so for each context image that does in fact share share 3D points with our query image, we would produce the E 3D tensor. So the representation network, this is the first component. So what we're looking at is 3 stacked input context images and their corresponding views passed to F, which is a convolutional neural network, and then to R, which is the representation. R then passes up to the epipolar geometry component, which was discussed in the previous slide. And then for each context image, we are producing our 3D tensor E, and these all get passed on to the next stage. The representations also get passed on, added together for each context image. So this is where the epipolar representation gets mapped to the generator. So we have our epipolar representations coming in as 3D tensors coming in from the top. And we have the H is providing the spatial positions, and then the attention map captures the weighted contribution for all of the tensors within three-dimensional tensors for each context image, feeds that back down to the convolutional LSTM, combined with the representation of the image itself, the context image from the previous slide. And so it keeps iterating like that. And the generator network is a skip connection convolutional LSTM, and it takes inputs from the previous slide, from the attention map of the specific areas of attention and their weighted contribution, feeds that into the skip connection LSTM, and as well as the previous hidden state, as well as the random latent variable Z. And so this iterates until we've generated a new image, and that new image is then compared to the ground truth for loss. So the second part of the contribution of this paper were the data set contributions, and it's OpenAI blocks, Disco humanoid, rooms random objects. And I'm not sure why disco, but could be because of the dancing like poses. So OpenAI blocks is based on the shadow hand robot with randomly generated joint configuration. It's a 20 degree of freedom hand robot, and so the letter cube is randomly placed in the hand, and the joint angles are random, and the lighting and the textures are all random as well, are all randomized as well. Now the constraints on the joint angles are similar to human physiological constraints, so that the joint angles are not don't randomly end up in a direction that fingers couldn't possibly go. Disco humanoid is based on the OpenAI GEM environment, humanoid version 2.0, and it's a 27 degree of freedom humanoid. And again, the joint angles are randomly produced, as well as lighting and textures for the scene are all randomly produced. Rooms random objects. So this is one of 4 objects from the ShapeNet database, and they're randomly dropped in the room. And the lighting, again, the lighting and the textures are randomly generated. And the constraint here is that the objects that are randomly dropped do not land in such a way that's physically or impossible. I think that was the only constraint to this one, similar to the hand. So for training, the GQN, this is the old data set, the previous data set, 64 by 64 images. The new data set is 128 by 128. GQN was batch size of 36. New data set 32. And it was models trained on 25 million examples. And that's the advantage of using 3D environment. You can produce as many as you like. So here's some qualitative results. And we can see that for each row here, we're looking at 3 input context images after the network has been trained. And the ground truth, the previous GQN and the new eGQN, this paper. And we can see distinct improvement, especially in the disco humanoid and rooms random objects. Here's more results. We have rooms free camera. We have 2 rooms free camera and Shepard-Metzler, which is the mental rotation test. And we can see that we do have improved results in all of them. So the only one that results in one of the qualitative results was the JCO did not seem to show as much performance gain from the new method. And we'll see that now. So maximizing the evidence lower bound. So the bottom of the charts is a minimized theoretical error. And we can see that there's usually an improvement except for JCO. And there's a possibility, I'm not sure if anyone has any insights into why JCO didn't do as well. But one possibility is that early in the paper, they talked about the benefit of epipolar geometry was that they'd be able to make sure that points distant from the query view that are in context images were captured and not lost in the convolution stages. And that was part of the thing to make sure that all the points that were on the epipolar line were captured, those features. And so the only thing I can think of is that JCO, JCO's robotic arm that picks up the ball, does not have a lot of distant points. All the points on the robotic arm are all within close spatial proximity. So that's why we might not see the advantages of the epipolar geometry. We can see more quantitative results here. We mostly did better than the previous method, except for rooms free camera. And so there is a reason that's possible. They didn't speculate as to why rooms free camera didn't do as well. But one possibility, and I'll go to the next slide. One possibility, so this is the previous method, the generative query network. And the generative query network is able to take multiple views, for example, of this maze, and then query a new view, which is the yellow, and build a fairly decent prediction based on that, which the yellow view had no previous images of that area. So there was no epipolar geometry that could have handled that. So I believe this is the type of situation that the epipolar geometry would not be able to handle. And this is possibly why the rooms-free camera, which is able to, I guess, randomly move in X, Y, and Z and get images from various places, is not getting enough, essentially, stereo images with the query viewpoint. And questions?